Today's discussion is about concavity. So what is concavity exactly? Well, concavity describes the shape of a graph, whether it be concave up or concave down. That is much different than whether something is just increasing or decreasing, because increasing and decreasing tells you direction, either it's rising or falling, whereas concavity tells you shape. In order to figure out if a function is concave up or concave down, you would look at the second derivative. The second derivative test from concavity tells you about if something is concave up or if something is concave down. If the second derivative is positive, then the original graph is concave up. If the second derivative is negative, then the original graph is concave down. Let's do an example. We're going to find the concavity of y equals 3 plus sine x over the interval from 0 to 2 pi. In order to find concavity, you need the second derivative. So you would go through the first derivative, and then find the second derivative. In order to figure out concavity, you're going to do the second derivative line test, just like we did the first derivative line test. So the first thing is to find the critical points. Set the derivative equals 0, solve. In this case, where is sine x equals 0? And that is where x is 0, pi, or 2 pi. Make your first derivative line test. I can see this is a closed interval. Pi is someplace in the middle. Go ahead and pick a point in this interval here, and also in this interval here, and plug it into the second derivative. So I have negative sine of pi over 2. That turns out to be negative 1, so that's negative. Put this into the second derivative. Sine 3 pi over 2 is negative 1, so this answer is positive. And what that tells you is that in this interval from 0 to pi, you are concave down. And in this interval from pi to 2 pi, you are concave up. Because we've switched concavity from concave down to concave up, at x equals pi, I have what I call a point of inflection. A point of inflection is where you switch concavity from concave down to concave up, or vice versa. When they ask you for a point of inflection, you want to go ahead and take that location you have found for x, plug it back into the original equation, and find your y value. That tells me my point of inflection is located at pi comma 3. Let's do another example. Given this equation here, I'm going to find concavity and points of inflection. Before we do that, I want you to take a moment, though, and see if you can find the places where this function's increasing or decreasing and where local maxes and mins are. Please pause the video and try those. Again, find where is f of x increasing, decreasing, and where are local maxes and mins. Okay, so far you should have found that the function was increasing from negative infinity to 0, or from 0 to 2, from 2 to infinity. You're decreasing from 0 to 2, local max at 0, 2, and local min at 2, -2. We're now going to determine the concavity and inflection points of the function. So in order to find concavity and inflection points, you're going to go ahead and take the second derivative. That is the derivative of the first derivative. So that would make 6x minus 6. Again, set that equals 0. Solve. And that finds a possible point of inflection. That's your critical value for your second derivative, so go ahead and put that onto a second derivative line test. So make sure you're putting it into the second derivative now and not the first. And I'm going to test 0, putting 0 into the second derivative. I found out that this comes out negative. Put in 2 in this area. This comes out to be positive. What that tells me, I am concave down in this interval from negative infinity to 1, and I'm concave up from 1 to infinity. That also tells me that since my concavity changed at that point, I have an inflection point, and that would be at 1, comma, and don't forget that you have to find f of 1, so you're going to go ahead and put this back into the original equation. 1 minus 3 plus 2 is 0. So the reason why I had you do all of that here is because now what you can do is you can actually curve sketch. You can use all this information to draw a pretty accurate description of this curve. I can do that because I know that I have a local max at 0, 2. I have a local min at 2, -2. And I have an inflection point at 1, 0. I also know that my function starts off increasing and concave down. And here at x is 1, it changes from concave down to concave up. Again, touching the local minimum and continuing on its way. We are skipping a couple pages of notes for today and just again reviewing that procedure for graphing. So the first thing you want to do, like we just did in that x cubed function, is we pictured kind of what it would look like. I know that x cubed does something like this. You find your first derivative. Your first derivative gives you your critical points. It tells you whether your graph is increasing or decreasing. It also gives you local max and min. Points of inflection occur where your second derivative is equal to 0. You would have concave up if your second derivative is positive. You would have concave down where your second derivative is negative. Don't forget that you also know asymptotes of curves from pre-calculus. You know how to find horizontal asymptotes and vertical asymptotes as well. After you've plugged in all of these key things, you can plot them on the graph and connect just like we just did.